Okay, we are going to look at this function and find the absolute extrema of this function on these different intervals. So remember, first of all, this word extrema means we're going to find the maximum and minimum values. And absolute extrema, or absolute maximum or minimum, means we are finding the highest output or the lowest output for the entire function. In this case, on these restricted intervals, not necessarily on the entire domain of the function. All right, so we have a theorem that says, it's called extreme value theorem, that says if we have a function that is continuous on a closed and bounded interval, which these are, so like an interval from A to B, including those endpoints, then we will have an absolute maximum and an absolute minimum value of the function on that interval. So the first thing that we might think about is whether this function is continuous on these intervals. And you might notice that this is a function with a denominator. And so in general, you have to be careful about functions like that and their continuity. So you might think about, does this denominator ever equal 0? And so if you solve that for x, you'll get x equals plus or minus I, which is an imaginary number. So there are no imaginary numbers in these intervals. These are intervals of real numbers. So the only places where this function would be undefined would be if we were considering imaginary numbers. But in general, in calculus, we are focusing on sets of real numbers for inputs for the function. So not for any real numbers. So this function is continuous everywhere, which includes on these intervals. So that theorem tells us that we will have an answer for an absolute maximum and an absolute minimum for this function on these intervals. Okay, so the answer is not none for any of these questions. All right, so then thinking about how to do that. So whether we're finding absolute extrema or local or relative extrema, we're going to start the same way. We're going to start by finding the critical points of the function or critical values. So to do that, we're going to look at where the derivative is 0 or does not exist in the domain of the function. And again, because that denominator is not ever 0, the domain of this function is all real numbers, negative infinity to infinity. Okay, so we're going to take the derivative, use quotient rule here. So derivative of the top times the bottom minus the top times the derivative of the bottom all over the denominator squared. All right, so there's our derivative. We want to think about where that derivative does not exist and where that derivative is 0. I'm going to start with the derivative not existing here. So in this one, because I have a denominator, the place where that derivative might not exist would be where the denominator is 0. We kind of already thought about that here. This denominator is slightly different than that one, but the same values that would make this denominator 0 would be what would make this denominator 0. So we don't have any of those on this problem. We do have some values of x, though, for which the derivative is equal to 0. All right, so sometimes I simplify our derivative before I set it equal to 0, and sometimes I don't. So that's a choice that you can make when you think about solving these problems. And you might think about which way you prefer to do the problems. The way you should prefer is the way that you're going to get through the problem without making a mistake. All right, so I'm going to go ahead and set this denominator, or not the denominator, the whole derivative equal to 0, and then solve it that way in this video. Sometimes I simplify them first. Okay, so at this point, we've been setting derivatives equal to 0 and solving for x enough that hopefully you should recognize what to do here. If you have a fraction equation, the first thing you want to do is probably clear the fractions. So multiply through both sides of the equation by that denominator. And on the left side of this one, where I have 0 times that, 0 times whatever is still going to be 0. And then when I multiply the right side of the equation by that denominator, the whole idea was that I would be able to clear the fraction from that. So that denominator would cancel with what I'm multiplying by, and I'm just going to be left with this numerator. 4 times the quantity x squared plus 1 minus 4x times 2x. I'm going to go ahead and simplify that. 4x times 2x is 8x squared. Okay, so now I just need to finish solving for x here. So there's some algebra involved here. However many steps of algebra you want to do is okay. I'm going to go ahead and write several steps out here, but if you can skip some steps and do that correctly, that's fine with me. All right, so I'm distributing through the 4 here. So 4x squared plus 4, and then I have the minus 8x squared. I have some like terms I will combine. So 4x squared minus 8x squared is negative 4x squared. So several different ways I could proceed from here. I'm going to actually add 4x squared to both sides of the equation so that I have positive coefficients everywhere. So that'll make those cancel. So I have 4x squared equals 4, and then divide through by 4. You do not have to write out all this algebra, but if you find that you're making algebra mistakes, then I would say think through and write out the algebra. All right, one more step here. So to get the x by itself, I'm going to square root both sides. And when I do that, remember that you need plus or minus the square root on the right side. And in this case, square root of 1 is just 1. So this one simplifies. Sometimes you end up with numbers here that don't simplify very nicely. All right, so I have 2 critical values. All right, so when we find local or relative extrema, our next step is usually to make a number line and test the signs on the derivative to determine where the function is increasing and decreasing. And you can do that here, but that's not enough to really answer this question. Because even if I know the function is increasing and decreasing, I don't necessarily know which point is the highest of the high points or the lowest of the low points. So it's not wrong to do that, but it will not get you to the answer that you're actually looking for here. So instead of making a number line and testing the signs, when I see this word telling me to find an absolute extreme value, I know that I'm going to do something a little bit different. What I need to compare is the y coordinates of the points at any place where I might have a possible extreme value. All right, so I'm ready to answer the question over here. For part A, I'm going to make a little table of values. And what I'm looking for is y coordinates of points. So those are going to come from the original function. Remember, not the derivative. The original function tells you points, xy points. All right, and so I'm going to use the x coordinates of the points that are actually in that interval. So I have 2 critical values here, x equals positive and negative 1. Only one of them is in the interval that we're asked about for part A. So x equals 1 is the only critical point. I'm going to use the negative 1 for some of these other problems that have different intervals that include negative 1. But for part A, I'm only going to have x equals positive 1. And then the other place where absolute extreme value might occur is at the end points of your interval. So the other values that I need to put in my table of values here are 0 and 5. All right, so I'm going to plug these values into the function, and then what I'm looking for are the highest and the lowest output values, y values. All right, so when I put in x equals 1, I'll have 4 over 1 squared plus 1 is 2, so 4 over 2 is 2. When I put in x equals 0, I'll have 0 over 1, which is 0. When I put in x equals 5, I'll have 20 over 25 plus 1, so 20 over 26, or that reduces to 10/13. You can get a decimal approximation if you want, but I don't necessarily care what the decimal approximation is. I'm just looking for the highest and the lowest output values here. So just recognizing that this is a positive number between 0 and 1, closer to 1. And so when I compare this output value with these other output values, I can see that this is the highest one. So this is the absolute maximum value of the function on that interval. And then this is lower than 10/13 and these other ones. So this is the lowest output value. All right, so for this part, our absolute maximum is 2, and it occurs at x equals 1. And our minimum value is 0, and it occurs at x equals 0. So just being clear about when they're asking for absolute extrema, they're really asking for the output values, but you might also be asked to indicate the x coordinate where those occur. All right, so to answer parts B and C, really, I just need to do a similar kind of thing here, make a table of values, and compare some x and y coordinates. All right, so for part B, both of my critical values, negative 1 and positive 1, are in that interval. And then I need to also consider the endpoints of this interval. All right, so when I put in these numbers, when I put in x equals negative 1, 4 times negative 1 will be negative 4. And then on the denominator, negative 1 squared is 1, plus 1 is 2. So negative 4 over 2 will be negative 2. I've already found the value when I put in x equals positive 1. I got positive 2. When I put in x equals negative 5, I will have negative 20 over 25 plus 1, 26. So negative 20 over 26, or negative 10/13, just the negative of this fraction. And I already found the value when I plugged in x equals 5. I got positive 10/13. All right, and then I'm just comparing numbers here. Again, decimal approximations are fine for these fractions because if you need them to help compare the numbers, but knowing that these are kind of close to negative 1 and positive 1, I can compare those with these output values and see here that I have a maximum value of 2. This is the biggest of these numbers, and that occurs at x equals 1, and a minimum value of negative 2, and that occurs at x equals negative 1. All right, part C, now I've done most of the work here. I just need to put the right numbers in the chart and choose the right values here. So for part C, I'm going to pick the critical number that's in that interval, x equals negative 1, negative 1. And then the endpoints of my interval, negative 5 and 0. And in my previous work here, I've got the y coordinates already, so I'm just going to copy those down. And then 0, we got 0. And comparing these numbers, so these are negative numbers and 0. So the biggest in this set of output values is this one. And then that occurs at x equals 0. And the lowest of these y values is this one, negative 2. And that occurs at x equals negative 1. All right, so the biggest confusion that people have on this is, like I said, people want to often make that number line like we were making when we were looking for local extrema. And that's not wrong, but it doesn't help you completely answer the problem because you need to determine not only the output values where you might have high points and low points, but compare those output values to see which one is the biggest of the high points or the lowest of the low points. So at some point, you need to make this XY chart where you're finding those output values of the function. The other thing that you might do on this is graph it on your graphing calculator and restrict your window to an interval that is stated here and look at that graph, and you should see the highest point and the lowest point on that window, and just to verify that your calculus is correct.